Welcome all. So, last time we started the multiple degree of freedom analysis method subjected to blast loading. In the previous class, we looked into the application of the design charts and applications of the numerical methods. So, we took up an example of a 2 degree of freedom system, and in the 2 degree of freedom system, we broken down into the free body diagram. From the free body diagram, we derived the equation of motion. From the equation of motion, we calculated the equation for the accelerations, and using these acceleration equations, what we were trying to do is that using different numerical techniques, we are trying to march with respect to time and calculate the total response of the system. So, the last time we took as one example where we are doing the average acceleration method. Okay. So, we wrote down the equation for the acceleration, we wrote down the equation of the velocity, and from the velocity we wrote down the equation for the response of the system. Okay. So, we will continue from that. So, continuing from the last time, what we can do is that we can substitute the previously calculated value. Okay. We can substitute the, so this was the average acceleration method. Okay. So, from the average acceleration method, what we did was for each mass, okay, we calculated the velocity. Okay. So, basically velocity we are calculating as if we have 2 points in the velocity curve. Okay. So, this is Vt minus 1, okay, and this is the acceleration is the slope. Okay. So, we are taking the average of the two accelerations, okay, At and At minus 1, okay, At and At minus 1, and we are calculating the average acceleration value. Okay. So, this is the average acceleration value, okay, and this thing we are adding into the previous velocity value, and from the previous velocity value we are adding it and getting the current velocity value. Okay. And this thing again we are substituting in the response, okay, the displacement of the system, and we are calculating the total displacement of the system, okay, from the previous values. Okay. So, if we substitute 4 in 3, okay, substituting 4 in 1a and 1b. Okay. So, from 2 to 3 we have come, 3 to 4 we have come, and now we got the equation for the 4, and 4 we are substituting in the equation 1 and 2. Okay. Okay. So, equation number 4, okay, this equation, okay, equation for the x we are substituting in 1a and 1b. Okay. If we do that, what we will get is this equation. Okay. So, this is nothing but equation 1a and 1b, where the values of 4 has been substituted. Okay. So, instead of writing x, okay, we have substituted the expression for the x. Okay. So, instead of writing x at time t, we have substituted the actual expression here out here. Okay. So, here we get the equation for the accelerations. Okay. So, the summary of the average acceleration method. So, how we are doing it. Okay. So, the total integration procedure is summarized as follows. Okay. So, first of all, we take at time t equals to 0, we compute the acceleration a1 naught, a2 naught using equation 5 and 6, okay, and specified value of x1 naught at t equals to 0 and x2 naught t equals to 0, velocity and forces. Okay. So, at time t equals to 0, okay, first of all you are using equation 5 and 6, and for the given values of x, displacement, velocity and forces, we are calculating the values of a1 naught and a2 naught. Okay. So, basically what we are doing here is that we are taking this equation 5 and 6, okay, we are putting the values of x, v, okay, and we are calculating a1 naught and a2 naught at time t equals to 0. Okay. We are calculating the values of f1, we are putting the values of f1, f2, okay, and all these values, okay, and we are getting a1 naught and a2 naught, okay, basically the values of acceleration at time t equals to 0. Okay. So, this is step 1. Okay. So, using 5 and 6 we are getting the initial values of the acceleration. Okay. After that we are marching in time. Okay. So, we know the values of a1 naught and a2 naught at time t equals to 0. Now, we are incrementing with delta time t. Okay. So, at that increment, okay, we are computing the values of A1 naught plus del t and A2 naught plus del t. Okay. So, here it was 0, here it was 0. So, now we are calculating at an incremental time del t, again using equation 5, 6 and the values of velocities and the displacements. Okay. So, we are going into the equation 3 and 4, we are going into equation number 3 and 4. Okay. We are calculating the velocities, we are calculating the displacements, putting it back again, okay, and again calculating the values of the accelerations. Okay. So, now we are making this in loop. Okay. So, we are now looping the step 2 and 3. Okay. So, now we are keep on adding del t, del t, del t, del t and calculating the accelerations. Okay. So, we are repeating step 2 and 3 until some specified time until the maximum value of the displacement is reached. Okay. So, if we keep on marching, what we will get is the values of the displacement, velocity and the acceleration with respect to the time t. Okay. So, now we have broken this thing into del t and we are marching with respect to time t. Okay. So, we can do this value until some specified time t, okay, if some t max is given, or we can do this thing until some maximum displacement is being reached. Okay. It should be noted that if x at time t equals to 0 and velocity at time t equals to 0, then the system will not move as long as f at time t equals to 0. Okay. So, here in the first step, okay, if everything becomes 0, okay, then the system is not going to move. Okay. So, there has to be either initial disturbance or initial force in the system in order to the system to respond. Okay. However, if f at time t equals to 0 is not 0, equation 5 and 6 will give an acceleration and the motion will start. Okay. Thus, the system of equation is self-starting and requires no special starting provisions. Okay. So, some sort of condition should be there in order to the system to get excited, either using the external forcing function or using some initial condition. Okay. So, this is how the average acceleration method works. Okay. So, we calculate the initial acceleration, okay, then we increment with respect to time t, we keep this thing in the loop until we reach our specified value of time t or we get the maximum value of time t. Okay. So, this is an easy method. Okay. So, using this method we can simply code it using in the Excel, or we can code it in MATLAB, make a small function and use it, or alternatively these methods, okay, average acceleration methods and other methods are already available as a function in Excel or as a function in MATLAB, which can also be used. Okay. So, depending upon what we are trying to do, we can write the program from the scratch also, or we can use the existing modules also to calculate the response of the system using any of the methods. Okay. Okay. So, average acceleration methods. Okay. So, now we are trying to do the same thing in the matrix method. Okay. So, mass m1, okay, displacement x1, at mass m2 the displacement will be x2. Okay. Spring constant k1 and k2, okay, external forces are f1 and f2, okay, and they come from the blast tributary areas. Okay. Damping we are neglecting. Okay. So, this is the mass matrix, okay, this is the displacement function, the forcing function and the stiffness value. Okay. So, this is the equation of the motion in the matrix form. Okay. So, blast loading, we are denoting the blast loading using a triangular pulse. Okay. So, basically this is how we are denoting the blast loading. So, this is the magnitude P naught, okay, this is the magnitude P naught and it is applicable till time capital T, till time capital T. Okay. So, till time capital T, this is the equation. After time t greater than t, it is 0. Okay. So, this is how the blast load is being specified. Okay. So, there is a peak pressure at time t equals to 0, there is a peak pressure at time t equals to 0 and it linearly decreases to 0 at time t equals to capital T, okay, and after that it remains 0. Okay. So, these are the system properties, okay, and this is the forcing function property, okay, and this is the equation of the motion. Okay. So, now we use the numerical integration in the matrix form. Okay. So, let us say we are using a time step delta t, okay, and let indices n denote time at t n. Okay. So, what we are saying is that we have broken down time t, okay, into discrete values of delta t, delta t, delta t, okay, and if we want to write time at any given value, okay, so let us say t n. So, t n will be number of increments times the delta t. Okay. So, matrix equation at time t n. Okay. So, this equation, okay, equation 4, the earlier equation 4, we can rewrite in the matrix form. Okay. So, if you remember equation number 4, okay, so this was the equation. So, this equation, okay, denoting the value of x calculated from the previous values of x, velocity and the acceleration, we are writing in terms of the matrix notation. Okay. So, this is the same equation, only thing is that it is written in the matrix form, okay, and this thing we are substituting it back into equation number 1. Okay. So, mxn, okay, k times x. So, the value of x is written out here, okay, equals to the forcing function. Okay. Then we collect the terms that multiply with the acceleration on the left. Okay. So, we have xn, this is one term, okay, this is the term. Then we collect this value, okay. So, this becomes, okay, so this two values, okay, fn is there, okay. Then we are taking this thing here, okay, and we are rewriting this equation. Okay. So, the effective mass term is, this is the effective mass term. Okay. Okay. So, continuing from there, similarly we use the same time marching method that we used previously. So, we are having an initial condition at x at time t equals to 0, it is 0, velocity is 0, acceleration is given by this term. Okay. So, then we assemble the mass matrix, stiffness matrix and compute again the A effective. We set the initial states and compute the initial acceleration, and for each time steps now we are marching in time t. Okay. So, del t, 1 del t, okay, 2 del t and so on and so forth. Okay. So, then we are calculating the values of the forcing function. Okay. As we march in time t, from the actual equation we are substituting the values of the forcing function. Okay. So, now we are evaluating the right hand side vector. Okay. So, this is my right hand side vector. Okay. So, this is the right hand side vector, and solving for this thing we can calculate the values of b, and again we update the values of the accelerations and update the values of the velocity and the displacement. Okay. And we keep on saving these values. Okay. So, in this way, okay, using the time marching scheme, okay, using the here the average acceleration method, we can solve the same problem in the matrix formulation. Okay. Okay. So, now let us put some numbers and let us try to do the solution. Okay. So, for the same example, we have taken mass as 200 kg, m1 and m2 as 200 and 300 kg respectively, k1, 2 and 1 Newton per meter, okay, raised to the power 10 of 6. Okay. Then the tributary area, okay. So, this tributary area we will multiply with the blast pressure in order to calculate our force. Okay. Basically, force will be P naught times the respective tributary area. Okay. So, this is the blast angular pulse. Okay. So, this is in terms of pressure. So, it will be multiplied with this tributary area to calculate the blast loading, and time is 6 milliseconds. Okay. So, P naught 6 milliseconds. Okay. And time step we are taking as delta time t as 10 raised to the power minus 4 seconds. Okay. And we will run the entire thing for the 6 milliseconds. Our loading is for 6 milliseconds. So, we will run the entire scenario for 50 milliseconds. Okay. Okay. So, this is the total time. Okay. So, then we make the mass matrix. okay. Diagonal matrix of diagonal terms are 0. So, 200 comes here, 300 goes out here, k. So, k1, k2, okay. So, okay, k1 plus k2, k2, okay. So, this is 2 plus 1, 3, okay, minus k2, minus k2, k2, okay. So, k1 plus k2, minus k2, minus k2, k2, okay. So, k1 plus k2, 2 plus 1, 3, and minus k2, minus 1, and k2, 1, okay. So, we made the mass matrix, we have made the stiffness matrix, okay, and forcing function, if we multiply by the tributary area, we will make the forcing function, okay. So, if we use the method out here, okay, so this is the solution what we will get, okay. So, here the blue line is showing the values of x1, okay, and if you remember we are calculating it for 50 milliseconds, okay. So, time stepping delta time t was 10 raised to the power 4 millisecond, okay. So, here you can see a smooth curve, okay. So, we can do this using Excel also, okay. We can do this using MATLAB also, okay. So, we have predetermined functions there, okay, which are already written down to take care of the average acceleration method. You can use that, or what you can do is that using this steps, okay, using the steps given out here, you can program the you can write your own code, okay, in MATLAB or in Excel to get the response of this system, okay. So, either the way I will request you to calculate the response and see whether it matches with our given solution or not, okay. Thereby you will be able to see for yourself the methods, okay. So, practice this thing, okay. So, this has been given as an practice problem, see whether you are able to reproduce the equivalent results, okay. So, moving ahead, okay. So, blast loading and its analysis, okay. So, an explosion or blast is a sudden and violent release of energy, okay. So, this is the Friedlander's profile, okay. So, here what happens is that there is a sudden release of energy, okay. What blast does, okay. So, blast causes a sharp increase in light and temperature, okay. So, the temperature will increase suddenly, okay. There will be an increase in the amount of light, okay, and there will be a massive increase in the pressure, which we can see from this Friedlander's profile, okay. So, in air, an explosion will create a plastic bulb that expands at the supersonic speed, okay. So, it will travel at a supersonic speed, okay. The released energy is distributed as thermal radiation, okay, heat energy, okay, which is shown by a sudden flash, okay, shock wave that is propagating in the air, and the shock wave transmitted into the ground and which expands radially, okay. So, this is how the blast energy, okay, or the blast loading interacts with the environment and it releases the total energy in the different forms, okay. Okay. So, here this is the propagation of the shock velocity, and if this is the point where the explosion is occurring, and if we move from this point, okay, we are looking into the same instant, time is same out here, okay. So, if we look into the different distances, okay, as we move outward from the place where blast occurs, we will see that there is a gradual decay in the pressure with distance, okay. This is the Friedlander's profile, what we are telling from the inception, okay. So, this is the ambient pressure, okay. So, a shock front forms, okay, and there is a sudden increase in the amount of pressure, okay, and with respect to time it will decay, okay. It decays and it goes beyond the ambient pressure, okay. It means that here suction increases, okay. So, thereby it is denoted as a negative pressure region. So, this is a positive pressure region and this is a negative pressure region, okay. So, here the suction will occur, okay. So, this is what we known as the Friedlander's profile, okay. So, from here, okay, what we do is that we make a simplified approximation of the pressure, So, what we do is we equate the total amount of energy, okay, from the actual blast to an simplified loading. Okay. So, in this way a simplified triangular blast pressure profile is being obtained. Okay. So, moving ahead. So, blast wave scaling law. Okay. So, according to the Hopkins blast wave scaling law, okay. So, in 1915 Hopkins proposed a blast wave scaling law. Okay. What he proposed was that if there are two explosives of different weights, okay. So, let us say one is made up of TNT and one is made up of RDX. Okay. So, this is TNT, let us say 1 kg of TNT and maybe 0.7 kgs of RDX. Okay. So, these are the different types of explosives. Okay. So, let us say there are two explosives of different weights, okay, two different explosives, okay, kind also, chemical composition also, and different weights also. Okay. If they produces similar blast effects at specified scale distances, okay, provided that the atmospheric conditions are alike. Okay. This concept is expressed through what is known as the Hopkins scaling distance. Okay. So, what he summarized is that if two explosives produces similar blast effect, okay, at certain specified distances, okay, given that the atmospheric conditions are alike, okay, then those things, those two signatures can be related and scaled in what is known as the Hopkins scaling distance. Okay. So, here in the scale distance or proximity factor, okay, so introduced a term Z, that is known as the proximity factor. Okay. And he expressed these things in terms of the R. R is the standoff distance, distance between the center of the explosion and the structure, or where the blast pressure is being calculated. Okay. Q is the explosive charge in equivalence of TNT. Okay. So, everything was expressed in terms of TNT, kg TNT. So, kg TNT is the base mass unit. Okay. So, it has two parts, one is the kg, okay, the weight of the charge, and TNT, the equivalent TNT charge. Okay. So, here everything, whether it is RDX, whether this is any other explosive, any other chemical based explosive, everything is expressed in terms of the equivalent amount of TNT. Okay. Here kg TNT does not mean that the explosives use is only TNT, it only means that the equivalent amount of mass is being used out here. Okay. So, there is another scaling law known as the SAS scaling law, okay, and it attempts to correct for the charges in atmospheric pressure. Okay. So, here there was a precondition that the atmospheric condition should be same. Okay. So, the SAS scaling law, okay, tries to correct for this point, okay, and it also tries to relate the proximity factor in different atmospheric conditions. Okay. So, now the scale distance, okay, R becomes a factor of the other factors also, or one additional term is there, E is the energy of the charge, and SAS law assumes that air behaves as a perfect gas. Okay. So, these are the two scaling laws. Okay. So, in this first scaling law, the atmospheric condition should be same, and in the SAS scaling law, the atmospheric condition, different types of atmospheric conditions are tried to relate it. Okay. So, here what does it mean? Okay. It means that the total amount of effect is same, okay, whether we take one charge, okay, and we calculate its effect at distance r1. Okay. So, if this is the effect, okay, and if we take, let us say this is 2 kg, let us say this is 5 kg, let us say this is 10 meter, and let us say this is r equals to 15 meter. Okay. So, if these two effects are same, okay, then this entire thing can be related using a what we know as the proximity factor, which is a function of the distance and which is a function of the weight. Okay. 1/3 is there because we are dealing in terms of volume. Okay. So, the total weight, okay, will be a function of the density times the volume. Okay. And the volume we are relating with respect to, volume is normally expressed in meter cube. So, if we take a cubic root, okay, so that is why 1/3 is being used. Okay. Root 1/3 is used out here. Okay. So, this is a way to relate the effect of the different explosions kept at different distances and using different masses. Okay. So, if the effect is same, everything can be related back using a proximity factor Z, and the Schatz's law also accounts for the different atmospheric conditions. Okay. So, types of blast loading. So, what are the different types of blast loadings? Okay. So, explosions are classified based on the detonation location. Okay. So, this thing we have already seen, and we are doing a quick review of this. So, there are air blast. Okay. So, in the air blast, detonation occurs above the ground surface. Underground blast, detonation occurs below the ground surface. Okay. Air blast types. So, air blast types can be further divided into air burst and surface burst. Okay. Free air burst occurs directly above the target with no interference before the blast wave reaches it. Okay. Wave reflection in surface burst. Okay. The blast wave reflects off the ground and merges with the incident waves, okay, creating a stronger hemispherical blast waves. Okay. So, the air bursts initially form a spherical wave front. Okay. So, the amplification effect, reflected surface burst increase the blast effect with a realistic amplification factor of about 1.8 due to the ground interaction and the energy loss. Okay. So, the amplification factor is approximated as 1.8 times, okay, and this is due to the ground interaction and the energy losses. Okay. So, these are a quick review of the different blast types, okay, which we have already seen earlier also. So, how to quantify the blast? Okay. So, the detonation releases a large amount of energy as blast waves. Okay. A large amount of energy is released as blast wave. Okay. And it causes a sudden rise in pressure, okay, positive phase. Okay. So, there is a sudden rise in pressure. Okay. The positive phase followed by a drop below ambient pressure. Okay. So, this is the atmospheric pressure on the ambient pressure, okay, P naught, and it suddenly rises, okay, and then there is a sudden drop below the ambient point. Okay. So, this is known as the negative phase, this is known as the positive phase, this we also can call as the suction phase. Okay. So, this is the negative phase and this is the positive phase. Okay. Both the positive and the negative phase contribute to the overall impulse of the explosion. Okay. So, the total impulse signature is a combination of the positive phase as well as the negative phase. Okay. So, for practical analysis, the blast load is commonly idealized as a triangular loading considering only the positive phase. Okay. So, what we do is that we take the total energy, okay, we keep the total energy of the system, okay, we keep the magnitude of the pressure same, okay, and then we try to equate with the area. Okay. So, here what we have done is that we integrate over the P times del T. Okay. So, and we equate now this thing using the same pressure times time T d positive. Okay. So, from here we can calculate our T d positive, which in principle has the same amount of impulse, okay, because the area for both the portions are same. Okay. So, we keep the same impulse area, we keep the same magnitude, and we calculate the equivalent positive phase duration. Okay. So, this is how for the practical analysis we convert from the actual blast profile of the Friedlander profile to an idealized triangular load considering only the positive phase duration. Okay. So, blast quantification. Okay. So, to quantify the blast, okay, there are different formulations, okay, proposed by different researchers depending upon the amount of data what was available to them at that particular point of time. Okay. So, there are many equations. Okay. So, to quantify the effect of the pressure, to quantify the effect of the time, okay, to quantify the positive phase duration, to quantify the negative phase duration, depending upon whatever the data was available at that particular point of time. Okay. So, here we are showing some of the widely used equations. Okay. So, one basic equation that is widely used is the Brody's equation. Brody's equation was proposed in 95. Okay. So it has a category for pressure in different ranges. Okay. So 0.1 to 10 bar, this particular equation is being used, and above 10 bar this particular equation is being used. Okay. So here one point is to be kept into consideration is that all these things are more or less an empirical approximations. Okay. So all these numbers, okay, which are being used, okay, they are very much unit dependent. Okay. Though z, the proximity factor, is being used, okay, here we can see the proximity factor has been used to normalize it, but this number should be used carefully and the actual unit should be maintained. Okay. Otherwise, if we change to different units, this will not make any sense. Okay. So if we want to use this particular equations, we will have to use these equations in their particular units only. Okay. Similarly, Newmark proposed in 1961 this particular equation, okay, where again we can see this is again an approximation, and again our proximity values are being used. Okay. So this is nothing but a form of z. Okay. Again these are given in bar. Okay. Similarly, Kinney in 85 proposed the following equations. Okay. What you can see here, it is interesting, is that the complexity of the equations is increasing. Okay. As we are marching in with respect to time, the complexity of the equations are increasing. It means that these factors, okay, they are trying to mimic the actual nature of the blast event. Okay. And since they are very complex, this is showing up in the equation becoming also complex. Okay. Similarly, in 83 Herald proposed one equation. Okay. Sadowski in 2004, he also proposed one equation. In 2010, Isadifard also proposed equations. Okay. So every researcher, depending upon the data that they could get, okay, they proposed step by step improvement on the equations, but at the end of the day, this is the same Friedlander's equation that it is being mimicked. Okay. And the shape of this Friedlander curve, okay, depends upon the nature of the blast used. Okay. So that is why you can see a lot of variation in the equations. Okay. So using these equations, we can predict, or we can try to predict the effect of the blast loading. Again, we have to use these equations in their respective units, because the factors that are being used are empirical in nature, and these are the correction factors which are being developed from the different experiments or different data that were available to the researcher at that point of time. Okay. So this equations gives a good approximation of the blast pressure profile. Okay. And this can be used in our analysis for any given system, but their zones should be known, okay, where it can be implemented, till what pressure range they can be implemented, and this equation should be used carefully depending upon the what type of data are being used. Okay. So here we are just showing different types of equation used. If we have to use them carefully, the limitation should be read properly and then used depending upon the particular cases that they are used in. So I will stop here. Thank you.